Hi, everybody. My name is Marissa, and I have a bachelor's degree in mathematics with a minor in statistics. In today's lesson, I will be discussing the sampling distribution for a sample mean, the conditions for the sampling distribution of the mean to be approximately normal, the standard error, and the relationship between sample size and the standard deviation of the sampling distribution of the mean. Let's imagine that we are the dean of a university and we are interested in the GPAs of the students that attend our university. We know that the average GPAs of our students are normally distributed with a mean of 3.24 and a standard deviation of 0.32. Every possible combination of mean GPAs we can obtain from samples of size n is called the sampling distribution of the mean. The mean of the sampling distribution of means, denoted by mu underscore x bar, is always equal to the population mean mu. The standard deviation of the sampling distribution of the sample mean, denoted by sigma underscore x bar, is equal to the population standard deviation sigma divided by the square root of n, our sample size. If we decide to take samples of 30 students, the mean of the sampling distribution of means would be 3.24, and the standard deviation of the sampling distribution of the means would be 0.32 divided by the square root of 30, which is 0.058. The sampling distribution of the mean will be normally distributed / bell-shaped if the sample came from a normally distributed population. However, if the population that the samples came from was not normally distributed, the sampling distribution of the mean will be normally distributed if the sample size is larger than 30. Although the mean of the sampling distribution of the means is the same as the population mean, the standard deviation of the sampling distribution of means differs. This is because sigma, the population standard deviation, measures the variability across individuals in the population. But the standard deviation of the sampling distribution of the means measures the variability across sample means. The calculation for the standard error is identical to the standard deviation of the sampling distribution of the mean, except we're using S instead of sigma. S is used as opposed to sigma when our population standard deviation is unknown. The formula for S, the sample standard deviation, is S equals the square root of the sum of x minus x bar squared divided by lowercase n, which is our sample size, minus 1. However, the formula for sigma, the population standard deviation, is square roots of the sum of x minus x bar squared divided by capital N, the total population size. As a result, we would get slightly different results for the standard deviation of the sampling distribution of the mean and the standard error of the mean. There is an indirect relationship between our sample size and the standard deviation of the sampling distribution of the mean, or the standard error of the sampling distribution of the mean. For the sake of simplicity, we will be discussing this concept in the context of the standard deviation of the sampling distribution of the mean. For our GPA example, let's calculate our standard deviation of the sampling distribution of means when we have a sigma value of 0.32 and a sample size of 10. This gives us a standard deviation of the sampling distribution of the mean of 0.101. Now let's say our sample size is 100 and keep our sigma value the same. This gives us a standard deviation of the sampling distribution of the mean of 0.032. The relationship between n and the standard deviation of the sampling distribution of means is indirect, because as our sample size increases, the closer and closer we get to the true value of the population mean. Let me explain why this makes sense. We know that on average, we have a 50% chance of getting heads when we flip a coin. If we flip a coin 3 times and all 3 times we get heads, the average number of times the coin lands on heads will be 100%. However, if we flip the coin 300 times, it is very, very unlikely that we would get heads all 300 times. This concept is known as the law of large numbers. As n increases, the closer and closer we get to the true value of the population mean. Because of this relationship, the standard deviation of the sampling distribution will decrease, because this results in less variability among samples of the mean. Let's see what we've learned today by doing a quick exercise. A daycare owner knows that the average age of the children who attend her daycare is normally distributed with an average age of 3.2 years old with a standard deviation of 0.3 years. If we take a random sample of 5 children, what would the mean and standard deviation of the sampling distribution of the sample mean be? Because the mean of the sampling distribution of means is just the population mean, 3.2 will be our answer for mu of x bar. For our standard deviation of the sampling distribution of means, we simply divide our sigma value by 0.3 by the square root of 5, and we get 0.134 as our answer. Great job, everyone! Today we defined the sampling distribution of the mean, as well as the conditions for the sampling distribution of the mean to be approximately normal. We also discussed the standard error of the mean, as well as the relationship between sample size and the standard deviation of the sampling distribution of the mean. Thanks for watching, and please be sure to check out other videos about statistics lessons and applications here on Chegg. Have a fantastic day, and I'll see you next time.